Imagine the entire universe squeezed into a space smaller than an atom. This tiny point, called a singularity, contained all the matter and energy that would eventually become everything we see today. Then, about 13.8 billion years ago, this singularity exploded in a fiery burst of energy known as the Big Bang. This wasn't an explosion in space, but rather the expansion of space itself. From this moment, the universe began to cool and expand, setting the stage for the formation of everything we know. The Big Bang is a fundamental concept in cosmology, the study of the universe's origin and evolution. It's supported by a wealth of observational evidence, including the redshift of distant galaxies and the existence of the cosmic microwave background radiation. The Big Bang theory explains how the universe evolved from a hot, dense state to its current state, and it continues to be refined as new discoveries are made. The early universe was a place of unimaginable heat and density where the fundamental forces of nature were unified. As the universe expanded and cooled, these forces separated and particles began to form. It's a story of incredible transformation from the tiniest of particles to the vast structures we see in the cosmos today. In the first fraction of a second after the Big Bang, something incredible happened. The universe underwent a period of rapid expansion known as inflation. Imagine a balloon with tiny dots drawn on it. As the balloon inflates, the dots move farther apart. Similarly, during inflation, the universe expanded at an exponential rate, stretching the fabric of space-time and smoothing out any initial irregularities. This rapid expansion is thought to have been driven by a mysterious force called the inflaton field. Just as gravity pulls objects together, the inflaton field exerted a repulsive force that caused space itself to expand at an incredible rate. Inflation is a crucial part of the Big Bang theory because it explains several observed features of the universe that were difficult to account for otherwise. For example, inflation explains why the universe is so remarkably uniform on large scales. If the universe had expanded more slowly, we would expect to see more variations in temperature and density. Inflation also explains the origin of the tiny fluctuations in the cosmic microwave background radiation, which are thought to be the seeds from which galaxies and other large-scale structures eventually formed. As the universe expanded and cooled after inflation, the energy of the Big Bang began to condense into particles. Imagine a pot of boiling water cooling down. As the temperature drops, steam condenses into water droplets. Similarly, in the early universe, energy condensed into particles of matter and antimatter. These particles were a mix of familiar ones like quarks and electrons and more exotic ones that no longer exist in the present-day universe. These particles were constantly colliding with each other, annihilating each other in a burst of energy, or combining to form new particles. This early universe was a chaotic and energetic place, but as it continued to cool, a crucial transition occurred. This transition was marked by the emergence of a slight asymmetry between matter and antimatter. For every billion pairs of particles and antiparticles that annihilated each other, a single particle of matter survived. This tiny imbalance, known as baryogenesis, is the reason why the universe today is filled with matter and not antimatter. For hundreds of thousands of years after the Big Bang, the universe was a hot, dense plasma where protons and electrons were too energetic to combine and form atoms. Light couldn't travel freely through this plasma because it was constantly being scattered by the free electrons. The universe was like a thick fog. However, as the universe continued to expand and cool, a crucial event occurred: recombination. Around 380,000 years after the Big Bang, the temperature of the universe dropped enough for protons and electrons to combine and form neutral hydrogen atoms. This event marked a profound change in the universe's evolution. With the formation of neutral atoms, the universe became transparent to light. The photons that had been constantly scattering off free electrons were now free to travel unimpeded across the cosmos. This first light is still detectable today as the cosmic microwave background radiation, a faint afterglow of the Big Bang. Section 5. The first stars ignite. After recombination, the universe entered a period known as the Cosmic Dark Ages. It was dark because there were no stars yet, and the faint afterglow of the Big Bang was gradually fading. However, Within the vast expanse of hydrogen and helium gas, gravity began to work its magic. Over millions of years, gravity pulled together clumps of gas, causing them to collapse under their own weight. As these gas clouds contracted, they heated up, and eventually the cores of these clouds became hot and dense enough to ignite nuclear fusion. The first stars were born. These early stars were massive and short-lived, much larger and hotter than the sun. They burned brightly for a few million years before exhausting their nuclear fuel and exploding as powerful supernovae. These supernova explosions enrich the surrounding gas with heavier elements, paving the way for the formation of more diverse and complex objects in the universe. Section 6: Galaxies, Cities of Stars. While stars were forming and dying, gravity continued to shape the universe on even grander scales. The first stars weren't randomly scattered throughout space, they were clustered together in groups called galaxies. Galaxies are vast collections of stars, gas, dust, and dark matter, all held together by gravity. These early galaxies were smaller and more irregular than the majestic spiral and elliptical galaxies we see today. Over billions of years, galaxies collided and merged, growing larger and more complex. Our own galaxy, the Milky Way, is thought to have formed from the merger of many smaller galaxies over cosmic time. Within galaxies, stars are constantly forming in giant clouds of gas and dust called nebulae. These stellar nurseries are where new stars are born, continuing the cycle of stellar evolution that began with the first stars. Galaxies are dynamic and evolving systems, constantly changing over billions of years. Section 7: Dark Matter's Gravitational Embrace. As astronomers studied the motions of stars and galaxies, they noticed something peculiar. There wasn't enough visible matter to account for the observed gravitational effects. Stars were orbiting around the centers of their galaxies faster than they should have been, and galaxies were moving within clusters as if they were being pulled by an invisible hand. This led to the hypothesis of dark matter, a mysterious substance that doesn't interact with light or other forms of electromagnetic radiation, making it invisible to our telescopes. Although we can't see dark matter directly, we can infer its presence through its gravitational effects on visible matter. Dark matter is thought to make up about 85% of the total mass of the universe. It acts like an invisible scaffold, providing the gravitational glue that holds galaxies and galaxy clusters together. Without dark matter, galaxies would fly apart due to the high speeds of their stars. Section 8: Dark Energy. The universe is accelerating expansion. In the late 1990s, astronomers made a groundbreaking discovery that revolutionized our understanding of the universe. By studying distant supernovae, they found that the expansion of the universe wasn't slowing down as expected due to gravity. It was accelerating. This unexpected discovery led to the concept of dark energy, a mysterious force that is thought to be responsible for the accelerating expansion of the universe. Dark energy is thought to be a property of space itself, causing it to expand outward even in the absence of matter or radiation. The nature of dark energy is one of the biggest mysteries in modern physics. It's thought to make up about 70% of the total energy density of the universe, but its origin and properties remain unknown. Understanding dark energy is crucial for determining the ultimate fate of the universe. Section 9: The Cosmic Microwave Background, a baby picture of the universe. One of the most compelling pieces of evidence supporting the Big Bang theory is the cosmic microwave background, or CMB, radiation. This faint afterglow of the Big Bang was discovered in 1965, and it provides a snapshot of the universe as it was just 380,000 years after the Big Bang. The CMB is a faint glow of microwave radiation that permeates all of space. It's incredibly uniform in temperature, with tiny fluctuations that provide clues about the early universe. These fluctuations represent the seeds from which galaxies and other large-scale structures eventually formed. By studying the CMB, cosmologists can learn about the composition, geometry, and evolution of the early universe. The CMB is a treasure trove of information about the Big Bang and the universe's infancy. Section 10: Our Place in the Universe. In the grand scheme of the cosmos, our planet Earth is a tiny speck of dust orbiting an ordinary star in the outskirts of a spiral galaxy called the Milky Way. Yet, despite our insignificant size, we have come to understand the universe's vastness and complexity through scientific inquiry and exploration. From our vantage point on Earth, we have discovered the laws of physics that govern the cosmos, witnessed the birth and death of stars, and unraveled the mysteries of the Big Bang. We are a product of the universe, formed from the same stardust that makes up everything around us. Our journey of cosmic discovery is far from over. With each new observation and scientific breakthrough, we gain a deeper understanding of our place in the universe and the incredible journey that brought us here. Section 11, The Future of the Universe, an Everlasting Expansion. The fate of the universe is ultimately determined by the interplay between gravity, which pulls matter together, and dark energy, which pushes it apart. The current understanding is that dark energy will win this cosmic tug-of-war, causing the universe to expand forever. As the universe continues to expand, galaxies will move farther apart, and the space between them will become increasingly empty. Stars will eventually burn out and new star formation will cease. The universe will become a colder, darker, and lonelier place. However, even in this distant future, the universe will still be a place of wonder and mystery. The laws of physics will continue to govern the cosmos, and new discoveries may yet surprise us. The journey of the universe is far from over. It's a story that's still being written.